Three things. Let's say we have some circle and there's some cable partially wrapped around it, or some rope, and on this rope from this side there's some weight. Let's say I call it W and it's 100 newtons. That's an approximation of 10 kilograms in Earth's gravity. So there's this load, 100 newtons, this weight at the tip of this wire, and on the other side we have some force F. Let's say a person pulling on the rope. And the goal is to make sure that this thing doesn't go down. So we're holding it in place. And there's this question, how big does F have to be? So if the friction is not taken into account, then there would be no question about it. But actually we will take it into account, and the answer is as follows. So there's some property with belts, and it's called belt friction. So as long as we have the friction between the material of a particular belt that we're considering, a rope, and such a round surface, we know there's as long as we have the coefficient of friction between these two surfaces, and also we can determine the angle of how much of the circle is the wire touching, which in this case it is, from the drawing might look more confusing than it really is, but actually if I locate the center, what is meant by the angle that is taken by the wire, how much is the wire wrapped around the circle, what it means is there's a point where the wire leaves the circle, stops touching it, and where it starts. And here it should be about 90 degrees. And so this is pi over 2. So pi over 2 is the angle for which the wire is around the circle. And this is an important piece of data that we will use directly in the calculation. So what I'm asking is how much force do we need here to pull here? How much force do we have to exert pulling on this wire from this side such that we hold this in place for the other side? And there's a direct equation for this in the context of belt friction. It is as follows. It is that in general it's written like this: T2 equals T1 times E to the mu s times beta or theta. Basically, the theta is the pi over 2, and the mu s is the coefficient of static friction, and the coefficient of static friction is different for different materials and always with a prominent stated. So let's say it's 0.5 for this case. All right. So that's it basically what we have to know. So we know the angle, and also we know the coefficient of static friction. And from this equation we can directly calculate it. We just have to identify what is T1 and what is T2. So the point is that this is supposed to help us. The fact that we have a cylinder or circle over which the wire is partially wrapped, and we're pulling over it and we're not pulling it straight directly, is because actually this will help reduce this required force, although the weight is still 100 newtons. So we can expect a smaller force here. And then there is this exponential factor, and then T2 and T1 should be explained. T2 and T1 are the forces on the opposite sides of the cable that is wrapped around that circle. So the point here is that this equation relates the two forces from the two sides of the cable to each other. And so if we know one force, we can calculate the other using this equation. And basically, this is the pulling force, and this is the force that reacts to that pulling from the other side. So this is like the active one. So for example, if I have this weight, well, the weight is pulling on the cable down here for 100 newtons, and the T1 that will be the T2, and then T1 tells us how much we will have to pull as this F. So if I was to translate the general T2, T1, that's the notation that's generally used, to this concrete example, it would mean that 100 newtons, or W, equals to F times E2, and now we can directly input the values. So coefficient of friction is a unitless value, and in this case it's 1/2. And in the exponent it's multiplied with the angle for which the rope is wrapped around the circle. So in this case it's pi over 2. Half circle will be pi, whole circle is 2 pi. So this is pi over 2. Alright, and this equation will directly tell us the solution. So W over e to the, and this can be simplified, pi over 4 equals F. So that's the idea. So F will equal to 100 over e to the pi over 4. Or it can also be written as 100 e to the minus pi over 4, and then the direct enumerated result you can do using your calculator. But this is the result. So basically it's interesting. We have an exponential function with base e, the Euler number, multiplying the weaker tension of the weaker side of the rope tension, and that equals the other side of the rope over the wrapping, behind the wrapping tension. So basically what we say here is that if we have some rope and we put on it, the other side will have a tension that is multiplied by this exponential factor, or this exponential function with base e, whose exponent is the coefficient of static friction and the theta. So we can say the higher is the coefficient of static friction and the higher is the angle, the more the tension will increase on the other side. So that's an interesting fact. And as we see, this will be 100 over something that is definitely higher than 1. And for that reason, we will get a smaller value for F than there is for W. So actually we will have to pull with less newtons than this wave was pulling over the circle. And once again, the angle we used here, we just put it right here, the angle we use here for theta is how much. So how do we identify the angle in a systematic way? There's a circle and there's a center. And I locate the points where the cable starts leaving the circle because of the wrapping. So it touches it fully here, but then it starts leaving it here, starts leaving it here. So from observation we see, in this case, when it's perpendicular pullings on these two sides, then by default this will be about pi over 2. And then there's cases if, for example, it was the F was down here in this direction, then the angle would be whole pi. And also it's possible if we have a cylinder that's longer, the cable can be wrapped more times. And then the angle can very much be more than even 2 pi, can be more rotation around the whole circle, it can be 10 pi for example. And that will very strongly increase the T2. So then there's exponential rise in the value of T2 because of T1 being multiplied by this e to something. Especially when the angle gets bigger and bigger, the amount of times that the wire is wrapped around. If it's high, then the actual tension on the other side will also be very high. So that's the idea. And also, last thing, this thing can be rewritten a bit. It also leads to the way that this equation was derived, which we did not talk about in this one at all. But if we have this formula, you can also divide T1 to both sides. And then you see that this E2, these two parameters, equals the ratio between the two tensions on the two sides of the cable over the wrapping around the circle.